Hello everyone and welcome back to JCE Connect. I am Professor Rajendra Jotawar from Jain College of Engineering. And today we will be continuing with the second model of cloud computing, that is architectures for parallel and distributed computing. We will be studying here parallel versus distributed computing, then we will be studying elements of distributed computing, under which we have general concepts and definitions, components of distributed systems, architectural styles for distributed systems, then we have models for interprocessing communication. Later we will be studying technologies for distributed computing, under which we have remote procedure call, distributed object frameworks, and service oriented computing. So without further ado, let's start with parallel versus distributed computing. The term parallel and distributed computing are often used interchangeably, even though they mean slightly different things. The term parallel implies that tightly coupled systems, whereas distributed refers to a wider class of systems, including those that are tightly coupled. The term parallel computing refers to a model in which computation is divided among several processors sharing the same memory. The architecture of parallel computing system is often categorized by homogeneity of components. Each processor is of same type and it has the same capability as others. The shared memory has a single address space which is accessible to all the processors. What does this mean? Basically, in parallel computing, let's say you have about 10 systems, 10 physical systems you have. All of them have the same configuration, the same processor, same storage and other things. Individually they will be separate. They will be the reason behind keeping the same processors is that in parallel computing, let's say you give a task, you have broken down the given task into smaller units or smaller parts or smaller problems. You will calculate that for a given unit of task it must take a certain amount of time. It shouldn't be like first computer is finishing the first task in the first stage, 10th system is finishing at the second, third system is finishing at the third. It shouldn't be like that. If a given task is supposed to be finished in the given particular time slot, it should be finished within that time slot. That is why in parallel computing we'll be having all the processors of the same capability, so that there shouldn't be ups and downs when the processing starts to work. When the tasks are given, it shouldn't be like the performance is going up and down. It should be same, it should be similar, it should be equal for all of those. When a program or a problem is given to the parallel systems or parallel computing, that program or that problem is broken down into several smaller units, which are then allocated to different processors so that they can communicate with each other. How do they communicate? In this parallel processing or parallel computing, there is one thing in common, that is the memory. For all those different 10 systems or whatsoever the number of systems, there will be a single shared memory, so that whatever the processing task they do and the resources they require, they can access it from the single memory itself. When a problem is given, it is broken down into different smaller units. Those smaller parts of problem is being assigned to one particular processor. That processor solves that given problem with the help of resources accessing through that shared memory. This is what makes parallel computing different from distributed computing. Coming to the distributed computing, the term distributed computing encompasses any architecture or system that allows computation to be broken down into units and executed concurrently on different computing elements, whether these processes on different known processes or the same computer or the cores within the same processor. Therefore, distributed computing includes a wide range of systems and applications than parallel computing, and it is often considered more general term. When a problem is given to distributed computing, it does the same. It breaks down the given problem into smaller pieces and allocates to the different systems. As I said, let's take the same example. Let's say we have the 10 physical computers all connected together, but in parallel computing the processors were similar, the configuration of systems were same, whereas they were also accessing the same memory. Whereas in distributed system, they will be of different configuration. Do you have 10 different systems? The configuration may vary. Processor, one will be faster, one will be slower. Of one system, let's say RAM is higher, another's storage is less. So there are 10 different distributed systems which are located at different places. It is not mandatory that they should be present at the one physical location. They can be spread across different places. They can be spread across buildings, towns, or even larger spaces as well. When a task is given, it breaks down to smaller pieces and it is assigned to different systems. When it is assigned, each of the computer or each of the nodes, each of the computing nodes accepts that given task and processes it and gives the single output. Even though it is not a rule, the term distributed often implies that the location of computing elements are not the same and such elements might be heterogeneous in terms of hardware and software. Next, we come to general concepts and definitions under elements of distributed computing. Now, as I stated in the previous class, we can say that distributed system or definition of distributed system can be put in together as a collection of independent computers that appears to its users as a single coherent systems. A distributed computing studies models, architectures, and algorithms used for building and managing distributed systems. Or in other words, a distributed system is one in which components located at networked computers communicate and coordinate their actions by only passing messages. That means distributed systems, as in the earlier example when I told you, they can be located at different places. They can be located at faraway places wherein they can be connected only through a network. That's also fine. Components that are located networked places communicate and coordinate their actions only by passing messages. When communication or coordination comes by passing messages, communication is another fundamental aspect that comes into picture of distributed computing. Since distributed systems are composed of more than one computer that collaborate together, it is necessary to provide some sort of data and information exchange between them, which is generally occurs through the network. And how is that done? We will be looking it into components of distributed system. A distributed system is a result of interaction of several components that travel the entire computing stack from hardware to software. It emerges from the collaboration of several elements that, by working together, gives users the illusion of single coherent systems. As we can see here in the diagram, it offers an overview of different layers that are involved in providing services of a distributed system. At the very bottom, computer and network hardware constitute a physical infrastructure. These components are directly managed by the operating system, which provides the basic services for interprocessing communication, that is IPC, process scheduling and management, and resource management in terms of file systems and local devices. Taken together, these two layers become a platform on which specialized software is deployed to run a set of networked computers into distributed systems. The top of distributed system stack is represented by the applications and services designed and developed to use the middleware. These can serve several purposes and often expose their features in the form of graphical user interface, that is GUIs, accessible locally or through internet via web browser. For example, in case of cloud computing, the use of web technology is strongly preferred, not only to interface distributed applications with the end user, but also provided platform services aimed at building distributed systems. A very good example is constituted by infrastructure as a service providers such as Amazon Web Services, which provides facilities for creating virtual machines, organizing them together into a cluster, and deploying applications and systems on top of it. Similar to this, you can see here the general reference architecture of a distributed system is contextualized in the case of cloud computing system. Note that the hardware and the operating systems layers make up the bare bone infrastructure of one or more data centers where racks of servers are deployed and connected together through high-speed connectivity. This infrastructure is managed by operating system, which provides the basic capability of machines and network management. The core logic is then implemented on the middleware that manages virtualization layer, which is deployed on the physical infrastructure in order to maximize its utilization and provide customizable runtime environment for applications. The middleware provides different facilities to application developers according to the type of services sold to the customers. These facilities offered through Web 2.2 range from virtual infrastructure building and deployment to application development and runtime environments. Next, we have architectural styles for distributed computing. Distributed system comprises the interaction of several layers. The middleware is one of that enables distributed computing because it provides the coherent and uniform runtime environment for the applications. There are many different ways to organize the components. The interaction among these components and their responsibilities give the structure to the middleware and categorize its type, or in other words define the architecture. Architectural styles aid in understanding and classifying the organization of software systems in general and distributed computing. Design patterns help in creating a common knowledge within the community of software engineers and developers as to how to structure the relations of components within the application and understanding the internal organization of software applications. Architectural styles do the same for overall architecture of software systems. Architectural styles for distributed systems are helpful in understanding the different roles of components in systems and how they are distributed across multiple machines. We can organize them into two major classes. First one is software architecture styles, second is system architectural styles. The first class relates to the logical organization of the software. The second class includes all those styles that describe the physical organization of distributed systems in terms of major components. Next, we have components and connectors. A component represents a unit of software that encapsulates a function or feature of a system. For example, it can be a program, object, processors, pipes and filters, etc. A connector is a communication mechanism that allows cooperation and coordination among the components. Differently from components, connectors are not encapsulated in a single entity, but they are implemented in distributed manner over many system components. Software architectural styles. These are based on logical arrangement of software components. They are helpful because they provide a view of whole system. Despite its physical deployment, they also identify the main abstraction that are used to shape the components of the system. The architectural styles are classified as per the below table. Data-centric architectures are the architectures that identify the data as the fundamental element of software systems and and access to the shared data is the core characteristic of data-centered architecture. Especially within the context of distributed and parallel computing systems, integrity of data is the overall goal of such systems. Repository and Blackboard are two most common architectural styles under this. Data flow architectures. In this case, data flow architecture, it is the availability of data that controls the computation. With respect to data-centered styles, in which the access of data is the core feature, data flow styles explicitly incorporate the pattern of data flow. Since the design is determined by orderly motion of data from component to component, which is the form of communication between them. Batch sequence and pipe and filter styles are the best example for this category. Virtual machine architectures. The virtual machine class of architectural style is categorized by the presence of an abstract execution environment, generally referred to as virtual machines, which simplifies the features that are not available in hardware or software. Applications and systems are implemented on top of this layer and become portable over different hardware and software environments as long as there is an implementation of virtual machines they interface with. The general interaction flow for this system implementation is the pattern as follows. The program or the application defines its operation and state of an abstract format, which is interpreted by the virtual machine engine, The interpretation of program constitutes its execution. It is quite common in this scenario that the engine maintains an internal representation of a program state. Very popular example for this category are rule-based systems, interpreters, and command language processors. Next, we have call and return architectures. This category identifies all the systems that are organized into components mostly connected together by method calls. The activity of systems modeled in this way is categorized by the chain of method calls whose overall execution and composition identify the execution of one or more operations. The internal organization of components and their connections may vary. Nevertheless, it is possible to identify three major subcategories which differentiate by the way the system is structured and how methods are invoked, that is, top down style, object oriented style, and layered style. At last, we have independent components. This class of architectural style methods systems in terms of independent components that have their own life cycles, which interact with each other to perform their activities. There are two major categories within this class, that those are communicating processes and event systems, which differentiate in the way of interaction among components is managed. At last, we have system architectural styles. These are the styles cover the physical organization of components and processes over distributed infrastructure. They provide a set of reference models for the deployment of such systems and help engineers not only have a common vocabulary in describing the physical layout of a system, but also quickly identify the major advantages and drawbacks of a given deployment and whether it is applicable for a specific class of applications. Here we will be looking at two fundamental reference styles, client server and peer to peer. In client server, in the given architecture of a client server, it is very popular in distributed computing and is suitable for wide variety of applications. As we can see here, client server models features two major components, server and a client, which interact with each other through a network connection using a given protocol. The communication happening between them is completely unidirectional. The client issues a request to the server. After processing the request, server sends a response. There could be multiple client components issuing the request to the server that is passively waiting for them. Hence, the important operations in the client server paradigms are request and accept at the client side and listen and response at the server side. Next, we have peer to peer. In this model, we can see here that it introduces a systematic architecture in which all the components are called peers, play the same role, and incorporate both client and server capabilities of a client server model. More precisely, each peer acts both as server as well as client. It acts server when it processes a request from the peer, as a client when it issues a request to other peers. In other words, all the systems connected in this architecture, in peer-to-peer architecture, plays both the roles, as a server, as a client. The peer sends a request to another peer. While sending it becomes a client. The one peer which is receiving it, it becomes a server. When it processes and gives the response, it is a server. The one which is receiving it, it is a client. At the same time, the same peer will be receiver for the another peer. So they play both the roles, as a server as well as client model. At last, we have models for interprocessing communication, also known as IPC. Distributed systems are composed of collection of concurrent processes interacting with each other by the means of network communication. Therefore, IPC is a fundamental aspect of distributed systems design and implementation. IPC is used either to exchange data and information or coordinate the activity of processes. IPC is what ties together the different components of a distributed system, making them act as a single system. Without IPC, the distributed systems which are located at far different places are even one beside the other. The main way of communicating each other is message passing. If they are not connected, if there is no communication happening between them, then the processes cannot happen. The motto behind the distributed computing is, even though they are physically different system, but they act as one. How do they do that? They do that by communicating through messages, by message passing. If there is no communication, there is no message passing. If there is no message passing, then they cannot act as a single system. There are several different models in which processes can interact with each other. These map to different abstraction of IPC. Among the most relevant that we can mention are shared memory, remote procedure call or RPC, and message passing. At lower level, IPC is realized through the fundamental tools of network programming. The most important reference models for designing the communication among the processes are message based communication and models for message based communications. Message based communication. The abstraction of messages has played an important role. The abstraction of message has played an important role in the evolution of models and technologies enabling distributed computing. In another way of defining distributed systems is one in which components located at networked computers communicate and coordinate their actions only by passing messages. The term message in this case identifies any discrete amount of information that is passed from one entity to another. It encompasses any form of data representation that is limited in size and time, whereas this is an invocation of a remote procedure or synthesized object instance or generic message. Therefore, the term message based communication model can be used to refer any model of IPC which does not necessarily rely on abstraction of data streaming. Several distributed programming paradigms eventually use message based communication despite the abstraction that are presented to developers for programming the interaction of distributed components. Here are some of the most popular and important: message passing, remote procedure call, distributed objects, distributed agent and active objects, and web services. The last one is models for message-based communication. We have seen how message-based communication constitutes a fundamental block of several distributed programming paradigms. Another important aspect of categorizing the interaction among distributed components is the way messages are exchanged and among how many components. In several ways, we identified client-server model as an underlying reference model for the interaction. This, in its strictest form, represents a point-to-point communication model allowing many-to-one interaction pattern. Variations of client-server models allow different different interaction patterns, which are point-to-point message model, publish subscriber message model, and request and reply message model. All three are sending request and getting response. For example, point-to-point unidirectional, one sends request, another gets response. Publisher and subscriber, there is single publisher, single server, many clients or subscribers. Publisher publishes it, clients get it. It is like getting a magazine. There is one publisher who publishes the magazine and different users or customers buy them. Request and reply message model is nothing but client sends a request, then a response comes. It is nothing like you can access it anytime. You have to send a request, that is a client has to send a request and get a reply. That's all for today. Thank you.